Today we are going to do defining heat. So let's go ahead and look at our ISM book here. So the first thing it talks about is give you the definition or defining heat as the energy that is being transferred. Energy transferred heat tends to move from an object at higher temperature to a lower temperature. It talks about a fruit juice in a can and how those molecules in the can move faster than the water that is on the outside that the can is floating in. So molecularly, fruit juice has a higher average kinetic energy than the water molecule, and that's what we're looking for now is the kinetic energy. So it talks about the higher the temperature difference between the two, the higher the rate of energy transfers between them as heat. So it gave you a scenario of winter compared to summer. They seem to be a lot different, but it's not with the temperature change. It also gave us the definition of what the different units of heat energy is and what it's equivalent to. And it also talked about what uses there are of those. And I just wrote those down because I know I've used joules before. That is going to be equivalent to 1 kilometer times meters per second divided by S squared. And then we have kilocalorie, a calorie like we use them for diet, a BTM, and thermal. And these give us the equivalent numbers for that. And then in the book, it basically talks about the difference between conduction, convection, and radiation. So it had a really good scenario here with the radiation is radiating from the fire here. Convection is inside of here, this water that's inside. And then conduction is something that's being touched. So if my hand was there holding the pot, that would be conduction. And then it gave us a conservation of energy. And it gave us a equation. So our equation for conservation of energy, which of course you know the triangle means change. That means the change in potential energy plus the change in kinetic energy plus change in internal energy should be 0. So we're going to use this equation and we're going to kind of change it some. So the first one that we're looking at will be in our textbook. They have a sample problem. That sample problem is on page 312. And what it says there, it says, and it gives you an arrangement similar to the one in demonstration energy conservation is shown on the right. A vessel contains water, paddles that are propelling by following masses through the water. This irrigation warms the water and increases the internal thermal energy. The temperature of the water is being measured, giving the indication that the water internal energy increasing. If the total mass is 11.5 kilograms, that's where we get that number from, 1.3 meters, that's the height, and all the mechanical energy is conserved into internal energy. By how is the internal energy of the water increased? And then we're going to also use gravity because gravity has to do with something with it. Now, this device here is a cylinder, and inside that cylinder there are paddles. Outside, we have something that has a kind of like a spindle on the top that you can turn. And then over here, you have weights on both sides. And as you turn it, it's causing this to spin. And it's asking us to find out what is the internal energy of the water that's increased. So what we have to do, first of all, is we have to look at all the 3 variables. This is the first one that we had here. This is the same one as that one there. And then we just changing it. Of course, the change in PE is potential energy final minus potential energy initial plus potential energy final. Kinetic energy final minus kinetic energy initial plus our change in U. And we're just changing the equation. We're going to put that in our calculator. There's not really anything special that we're doing here. So, only thing we're doing is open bracket 11.5 times 9.81, which is gravity, times 1.3, and that will give us 146.6595, but then it has it in scientific notation. So if we want to go in and change it into scientific notation, That's where I get my 1.5 10 to the second, because the number that I have there is 1.466595 E2. So either 146.6595 would have been okay, but I would prefer 1.5. So now what we're going to do is we're going to do our practice problems. They're not very hard at all. So let's look and see what it says. It says the arrangement described in sample B. We're doing the same arrangement. How much water internal would increase if the mass was at 6.69? So we're keeping everything the same except we're changing this to 6.69. You're doing the same thing you did before by multiplying, and you should get 755 joules. Number 2, a worker dives at a 0.500 kilogram spike. That's my mass of my spike. And a railroad tie at 2.5 kilometers sledgehammer. So there is my mass of my hammer. Okay. And it says the hammer strikes at a speed at 65 meters per second. Well, that's my speed, right? If 1/3 of the hammer of kinetic energy is converted into internal energy of the hammer spike, how much is the total internal energy increased? So we're going to do 1/3, right, of kinetic energy times E times H, which is also equals to this. So we're going to take our number for our mass of our N, which is 2.50, and then we're going to take our velocity, which is 65, which is our speed, and square it, and we're just going to put that in the calculator. So with that, you can do alpha y enter. You can do 1/6, open bracket, 2.50, close bracket. That is 65.00, close bracket, and we're going to square that. And then we get 1.76 times 10 to the third joule. Okay. Number 3, a 3.0 times 10 to the negative 3 kilogram copper. That's the mass. Drops a distance of 50 meters to the ground. That's the height. If 65% of the initial potential energy goes into increasing the thermal energy of the penny, determine the magnitude of the increase. So we're going to take our 65%, we're going to change that to a number. So we're going to take our 65 times our mass times gravity times height. So the only thing we're doing here is we're just doing this 0.65, 3.0 times 10, carats and negative 3 over and back down. Gravity and our mass. Our height, excuse me. And we get 9.56 times 10 to the negative 1. If we change that mode to normal mode, which I will accept either answer, and that's where I get 0.96 because my answer is 0.9565. Okay? And then number 4, the amount of internal energy needs to raise the temperature to 0.25 kilograms of water at 2 degrees Celsius at 209.3. How fast does 0.25 kilogram ball travel in order for its kinetic energy to equal the internal energy? So this one here, instead of doing half of the mass times velocity squared, we're going to do the square root of 2 times the change in V, change in U, excuse me, over M, and we get 41 meters per second. Okay, so the last thing I want to talk about is the quiz that you have for section 1 that you have today that you need to also do. So I want to make sure that if you're watching the video, you get a benefit for that. Number 1 and 2 and 3 are just basically notes that we have taken about a definition of what heat is. I don't think that's very hard at all. Number 4 talks about the energy transfer spontaneous from the heat of a substance, and that will be C. Number 5 is D. Number 6, you can pretty much find out for yourself. Number 7 has to do what an insulator is, which is B. And then for number 8, you have to use this equation here to find out what you think it is, which, by the way, the answer's there. Number 9, you just have to kind of like explain what that is going on there. And here is your equation. You're going to be using this. So you're going to take this divided by this times that to get your answer. I hope that if you did watch this video, that you got some help today on the quiz that you have to do this afternoon. And God bless you, and I love you, and I can't wait to see you again.